4.16. For a circular coil of radius r and n turns carrying a current I, the magnitude of the magnetic field at a point on its axis at a distance x from its center is given by B equal to mu 0 I r square n upon 2 into x square plus r square raised to 3 by 2. Question A. So that this reduces to a familiar result for field at the center of the coil. B. Consider two parallel coaxial circular coils of equal radius r and the number of turns n carrying equal currents in the same direction and separated by the distance r, so that the field on the axis around the midpoint between the coils is uniform over a distance that is very small compared to r, and is given by B equal to 0.72 mu 0 n I upon r approximately. Such an arrangement to produce a nearly uniform magnetic field over a small region is known as Helmholtz coil. Okay. Now, first question A. So, equation of the magnetic field at any point on the axis of the current carrying coil, that is given by mu 0 I r square n upon 2 into x square plus r square raised to 3 by 2. Now, at the center of the coil, we can take the distance of the point from the center of the coil, that is 0, means x equal to 0. So in this equation, if we substitute x equal to 0, then we will get B equal to mu 0 I r square n upon 2 into 0 plus r square raised to 3 by 2. Now here this r square raised to 3 by 2 will resultantly give you r cube. And now if r square cancel, then 1 r will be there in denominator. So your equation turns to n mu 0 I upon 2r. This is the equation for the magnetic field at the center of the current carrying coil. Clear to all of you? Now question number B. So here we have two coaxial coils having radius that is equal to r, number of turns in each that is n, and these two are separated by distance r. Now we have to prove this thing. Now at the midpoint of the axis of these two coils, right, the magnetic field that is uniform in the region close to the midpoint. Okay. Now see, here midpoint means from each coil it is at distance r by 2. And now we have to consider another point which should be very close to this midpoint. So here consider that another point at a distance d from the midpoint as shown in the figure. It implies that now from the center of the first coil, our decided point that will be at distance r by 2 plus d, and for second one it will be r by 2 minus d. Now in our equation, mu 0 I r square n upon 2 into x square plus r square raised to 3 by 2, in that equation, x is replaced by r by 2 plus d for first coil and r by 2 minus d for second coil, and mu 0 I r square by n, that is common from the equation of fields of both the coil, current through both the coil that is in the same direction. So field at the axis will be in the same direction. So resultant field, that is the summation of these two. And this denominator part that is written in the numerator, so its power is taken as raised to minus 3/2. Clear up to this one? Now, mu 0 I r square n by 2 outside the bracket as it is. Now simplify this. R by 2 plus d whole square as r square by 4 plus rd plus d square plus this r square as it is and whole raised to minus 3/2. Plus, now simplify this r by 2 minus d whole square as r square by 4 minus rd plus d square plus r square raised to minus 3/2. Now, mu 0 I r square n by 2 as it is. This r square by 4 plus r square, that you can write as 5 r square by 4 plus rd plus d square as it is and raised to minus 3/2. For this second bracketed term, you can write again r square by 4 plus r square, that is 5 r square by 4 minus rd plus d square as it is and this whole raised to minus 3/2. Now, mu 0 I r square n upon r, that is as it is. Now from these two terms, suppose we take 5 r square by 4 common. Now if we take 5 r square by 4 common, then at the place of 5 r square by 4, you can write 1. For this rd, now from rd, if you take 5 r square by 4 common, then you have to multiply it by 4 upon 5r. Because see, if you multiply this 4d upon 5r by 5r square upon 4, then again you will get your answer rd. And here, in the question itself, it is given to you in the region very close to the midpoint. We have to derive the equation for magnetic field. Means d, that is very small compared to r, and therefore d square is neglected compared to other terms. Clear to all of you up to this one? Now, mu 0 I r square n by 2. Now, here this r square raised to minus 3/2 will give you r raised to minus 3. So when you write it in denominator, then that will be r cube. And this 5/4 raised to minus 3/2. So you can write it as 4/5 raised to 3/2. Now, here for these bracketed terms, you can use binomial theorem for simplification. Now, in binomial theorem, the power is multiplied with this second term. So, 1 minus 3/2 into 4d upon 5r plus this 1 and minus 3/2, so plus 3/2 into 4d upon 5r. So see here, minus 3/2 4d upon 5r and plus 3/2 4d upon 5r. These two will be cancelled. And this 1 plus 1, that will be 2. So you can write mu 0 I n, this r square upon r cube, that is r, these 2 as it is, 4/5 raised to 3/2, 2 cancelled. So mu 0 I n upon r into 4/5 raised to 3/2. And now if you solve this term 4 by 5 raised to 3 by 2, then it will come to approximately 0.72.